Glad to be here today. I'm Rob Schapire. I'm going to talk about theory of multiclass boosting. I guess I first met Partha, it must have been around 1990 or so, and we were at MIT together, and then later we were at Bell Labs together, although as it happened, we never actually collaborated together. We were never actually in the same group, unfortunately. I also wanted to feel the need to mention why this memorial conference, coming as it does, is especially poignant for me on a personal level. As everybody knows, Partha died of a brain tumor, and it happens that my sister also has a brain tumor that we've known about for about 3.5 years, and let's just say she's not doing very well right now. This was, I don't know why the Mac does this to me, but this is all of us at an event that's held for people with, to support people with brain tumors and to raise money for research for brain tumors. My sister is the one in the yellow there. We're there with my family and her family, and also this is my cousin Walter, whose father, my uncle, also died of a brain tumor, so it's a really nasty illness. This was taken in May, so it's a very moving type thing to be there with all these people who have brain tumors and remembering people and so on. It's very moving, very heartbreaking also. And you know, in addition to being there for my sister, I was also thinking a lot about Partha, of course. Anyway, see, and then it goes back and does that to me. Okay, so on to the talk. So I'm going to be talking about a theory of multiclass boosting. I wish I could be giving a talk about something I did with Partha, but like I said, we never got to collaborate, unfortunately. This is joint work with a student, Indranil Mukherjee, former student. He graduated in August. So I'm going to be talking about boosting. I know many of you know about boosting. I know some people here are experts on boosting, but I understand that it's also a broad audience, so let me just start at the beginning. So we're looking at classification learning problems. So we're looking at a problem like this one, where you have some kind of example, some objects that we're trying to categorize. So like in this case, we're trying to categorize headlines, newspaper headlines. So the first one, Tea Party convention is canceled. We're trying to classify it by its main topic. So that one's about politics. NBA aims to rein in players whining is about sports, and so on. So we're just trying to categorize or classify objects of some kind. Not necessarily text, could be any kind of objects. This is just an example. So if you think about a problem like this, you could imagine that it would be easy, in principle, to find kind of weak classifiers for data of this kind. So a weak classifier might be something like this, that, you know, something pretty simple-minded that says, well, if the word game occurs in the headline, then predict it's about sports. Otherwise, make some other arbitrary prediction. Maybe predict that it's about politics. So, you know, it's reasonable that that could do a decent job. So, you know, if it has the word game, it probably is about sports. If it doesn't have that word in it, then who knows what it could be about. Politics is kind of just a guess. And even if game is in there, it could be about something else. It could be about game theory, about, you know, then it would be, what, science and mathematics or something. So the idea is that a rule like this can at least be better than random guessing. It's doing something which is not entirely trivial. So the idea of boosting is to take a whole bunch of these weak classifiers and to combine them into a single rule that we hope will be very highly accurate. So the way that boosting algorithms work is that we find many, many of these weak classifiers of some kind. Each one is trained on a different distribution over the training set, and then we combine them into a single rule that we hope will be very highly accurate. Okay, so this is so as with most learning algorithms, boosting is based on an assumption. some assumption that we're making about the world or about the data. So in boosting, the assumption, that core assumption, is called the weak learning condition. And all of the theory of boosting is based on that assumption. It's this assumption that the weak classifiers that we found are all a little bit better than random guessing. And given that assumption, a boosting algorithm is one that we can prove will have arbitrarily small error, arbitrarily high accuracy. That's why it's called boosting, because you're going from kind of crummy, mediocre accuracy to very high accuracy. And the idea is that we want to assume as little about the weak learning algorithm, about these weak classifiers, as possible. So we want that condition, the weak learning condition that we're basing things on, to be as minimal as possible. Okay, so there's an awful lot known in the binary case. Boosting algorithms, like an awful lot of learning algorithms, were developed for the binary case, for the case where we have just two possible classes. So, spam or not spam, good or bad, positive or negative, where you just have two classes. And in that case, the theory is very well developed and very well understood. In the multi-class case, where you have more than two categories, which in many ways is more realistic, there's a lot which is unknown, and which we tried to answer in this work. So that weak learning condition in the binary case says you should just be a little bit better than random guessing. And you would think that something like that would just immediately generalize to the multi-class case. But it turns out that it doesn't. In the multi-class case, we have many possibilities of what that weak learning condition can be, and kind of the obvious choices don't work at all, as I'll talk about later. So it leads to the question, what is the right weak learning condition in the multi-class case? And what that's really saying is, what is the least that we can assume about the weak classifiers, about the weak learning algorithm, for boosting still to be possible? And this is related to the notion of efficiency, because we can also ask, how can we boost with optimal efficiency? In other words, how can we get the most out of a weak learning algorithm while assuming the least about it? Okay, how can we get the most out of the weakest of all possible weak classifiers? So I'm going to be focusing in this talk mainly on what happens on the training set itself, but this is also relevant to generalization. By generalization, I mean how well we do on data that was not seen in training, on new data that eventually comes in. So, well, first of all, if we can find a way to use weaker weak classifiers, if we can use simpler rules, then those simpler rules will often be less prone to overfitting. And this is a theme that's seen over and over again in learning, that simpler rules, if you can use them, will often work better. There will be less overfitting. And secondly, if we can come up with boosting algorithms which are more effective, which do a better job of fitting training data, then that might make underfitting less likely, because a corresponding problem is that you don't even fit the data that we have. Okay, so here's what I'm going to talk about. I'm going to talk about a new framework for studying multi-class boosting. What we found is a whole family of weak learning conditions. As I said, there are many, many possibilities of weak learning conditions. So we found one family, which I'll talk about, which requires performance that only is a little bit better than random, okay, which is what we want. And each of these conditions is sufficient for boosting. And taken as a whole, we can show that this family is as weak as possible. So this is kind of what we're looking for. This is for an entire family of weak learning conditions. We've also found, where you have to kind of consider the entire family as a whole, we've also found a single weak learning condition which has similar properties and which is by itself minimal. It's a little bit more complicated to work with. We've been able to characterize a lot of the conditions that are found in the literature. So there are many multi-class extensions of boosting. Many of them are based on various kinds of assumptions, often not explicitly stated. But we've been able to go back through and categorize most of them, and most of them turn out to be either too weak or too strong. They're just not exactly the right assumptions, as I'll explain. We'll talk a little bit about algorithms and experiments. Okay, so let me start by talking about the case of boosting in the binary case, where we just have two classes. So as is typical with classification learning, we assume that the learning algorithm is given a data set. So we have M training examples. Apologies to the statisticians in the audience who use N. So M for the number of training examples. Each training example is a pair, xi, yi. So xi is the object that we're trying to classify, and yi is the label. It comes from some space, capital Y. So in the case of binary data, there are just two possible labels, and it's convenient to call them +1 and -1. Now, boosting takes place in rounds. So there are capital T rounds altogether. On each round, we're training a weak classifier. What actually happens is that the booster chooses a distribution, dt, over the M training examples. These are the indices of the M training examples. And in response, the weak learner selects a classifier, a weak classifier, ht, which is just a prediction rule. It just assigns a predicted label to every one of the possible examples. Okay? And here's the weak learning condition that I talked about before, which basically just says that we have to do a little bit better than random guessing. So in other words, here's our weak classifier, ht. And what we're doing here is we're measuring the error with respect to the distribution dt. So we're just computing the probability that this weak classifier misclassifies an example, xi, yi, when that example is chosen according to the distribution dt on which it was trained. So it's just the weighted training error of that weak classifier. And what we want is for it to be better than random guessing. So if you guess randomly in a two-class problem, you'll be right exactly half the time. So we want the error to be at most a half minus a little bit, minus some small positive number gamma. So we want the weighted error to never be more than 48%. Okay, and then at the end of the day, after we've gone through this cycle, capital T times, the booster outputs a majority vote classifier. So some of you probably are aware that there are other boosting algorithms that output other kinds of classifiers, especially weighted majority vote classifiers. Here I'm just keeping things simple and assuming that we're outputting a simple majority vote classifier. So what that means is that given an example X, what this final or combined classifier does is it evaluates all the weak classifiers. Each one predicts +1 or -1, and it takes a majority vote. So one way of writing that is that it just adds up the predictions, and if the sum of the predictions is positive, predict +1, otherwise predict -1. Or here's another way of writing it. Just choose the label that gets the most votes. Okay, so I assume this is, based on the abstracts, I'm guessing that this is new to some people. So let me just quickly go through a very quick concrete example. So in this case, there are, the examples are points in the plane, and there are 5 positive examples and 5 negative examples. Now, I didn't say how the booster computes this distribution. I didn't actually specify a boosting algorithm. But a typical algorithm will tend to put the most weight on the examples that have been most classified the most. So on the very first round, nothing has happened yet. So we can just give equal weight to each of these 10 classifiers, each of these 10 examples, rather. And the weak classifiers here will be vertical or horizontal half planes, as you'll see what I mean in a second. Okay, so we pass off this distribution over the examples to the weak learning algorithm. It gives us back a weak classifier, such as this one, H1, which classifies everything to the left of the line positive, everything to the right of the line negative. So that weak classifier misses 3 of these 10 examples. Okay, so its weighted error, since they all have equal weight, is 30%. Now, as I said, a typical boosting algorithm will increase the weight of these incorrectly classified examples and decrease the weight of the others. So these three examples will get larger weight under the next distribution, and the others will get smaller weight under that distribution. Then we do it again. We find a second weak classifier. This one classifies everything to the left positive, everything to the right negative. This one misses these 3 points. So they get higher weight under the next distribution, D3. And now you can kind of see what's happening here, because these 4 examples out here have really low weight. They have low weight because they were correctly classified on the first 2 rounds of boosting. So on this third round, they're almost ignored. And so you can see what the weak learner is going to do on the third round is choose a weak classifier like this one, which says everything above positive, everything below the line negative, which misses 3 of these examples, but we don't really care about them because they have low weight. All right, so now if we take, for the final combined classifier, what we do is we take these 3 weak classifiers, H1, H2, H3, add them up, take their sign, which is to say just take their majority vote of the 3 of them. And what we end up with is a combined classifier which does something more complicated, which predicts everything in this blue region positive, everything in the pink region negative. Okay? And so what happened here is that we used these 3 weak classifiers. Each one missed 3 out of the 10 examples, 30% of the training examples. But in only 3 rounds, we drove the training error to 0. We got perfect accuracy on the training set. Okay, so as I said, what I'm really focusing on in this talk is this weak learning condition. And I want to emphasize how that weak learning condition is really the basis for the development of boosting algorithms and their theory, especially in the binary case. So a boosting algorithm that, the first practical boosting algorithm was one called AdaBoost. I'm not going to talk about it in detail, but I will mention it several times. So suppose we run AdaBoost for T rounds. So let's see how the weak learning condition applies to AdaBoost and understanding what AdaBoost does, how well it performs. So first of all, if the weak learning condition holds, if that condition that I talked about before holds, then the training error of the combined classifier H can be proved to be at most e to the minus 2 gamma squared t, where gamma, again, is that edge, how much better than random guessing we're doing, which means the training error goes down exponentially fast given the weak learning condition. Okay, so what else? Well, this means that if we choose the number of rounds to be something like this, then the training error will fall below 1 over m, the number of examples, which means that the training error will actually be 0, again, given the weak learning condition. And the fact that it's driving down the training error that quickly means we can also prove something about its generalization error. We can show that its generalization error will go down like something like d over gamma squared m, where d is some measure of the complexity of the weak classifiers, like VC dimension would be a typical measure of complexity. If you don't know what that is, it doesn't really matter for this talk. Okay, and there are other styles of analysis. So if we, instead of stopping the algorithm after this many rounds, we let it run to convergence, so to speak. There's another method of analysis based on what's called the margins theory, which basically says, again, if the weak learning condition holds, then not only will all of the training examples give correct predictions, but those predictions will also have high confidence. They'll have large margins, where margin is a measure of confidence. And that translates into another bound on generalization error that actually turns out to be fairly similar to this one. Okay, so the point is not the details of these bounds, but the point is that the analysis is based on this assumption. And that's really at the heart of the theory. Okay, so given the reason why we've all come to this conference, I wanted to mention some work that Partha did, which actually gives an alternative approach to understanding boosting. So the approach that we're taking is to start with the weak learning condition and to analyze boosting based on that assumption. So Partha, and work that he did with a student that he had at the time named Sandy Cooten, what they did was to analyze AdaBoost in particular using stability theory. So there are various ways of measuring what's called stability in a learning algorithm, but the basic idea is to measure how much the classifier produced by a learning algorithm changes when the data is perturbed. So there are various ways of perturbing the data set. You know, for instance, you could remove one example and replace it with another example, and then rerun the learning algorithm. And if you do that, you'll end up with a slightly different classifier, and then you can look at how much it changes. And if it doesn't change a lot, you say that the classifier is stable. Again, various ways of measuring this. And a lot of those definitions turn out to be sufficient for generalization. So you can show if a learning algorithm is stable, then it will generalize well. And in some cases, in work that was done with, by Partha and his collaborators, Tommy Poggio and others, there are various cases that where you can show that this is actually necessary. You can essentially show that learning and stability are actually the same in a certain sense, equivalent in a certain sense. Again, I don't want to go into the details here, but Partha and Sandy were the first to apply this theory to AdaBoost. And so their approach to analyzing AdaBoost was very different. They started out with the assumption that the weak learner is stable, that it's stable and that it satisfies a certain weakness condition, a little bit different than what I'm talking about now, but related. And given that assumption, they were able to show that AdaBoost will also be stable. And because it's stable, they could then bound the generalization error without appealing to VC theory, which is kind of nice. Unfortunately, the bounds they ended up with were fairly weak, and they left it as an open problem to improve on those bounds. It's kind of interesting to contrast what they did with some of the other approaches to boosting that have been proposed over the years. So they assume that the weak learner is stable, and they use that assumption to show that AdaBoost will also be stable. But really what they're showing is that the boosting process does not lose stability too quickly, which is kind of why their bounds are a little bit weak. It's interesting to compare that with the work of Leo Breiman, work that he did years ago, where he argued that AdaBoost works by stabilizing an unstable weak learner. So his approach was almost the exact opposite of what Sandy and Partha did. So he started out by saying, well, actually, the case where boosting is going to be most effective is when the weak learner is unstable. And the reason that boosting works is because it adds stability. And that increase in stability is actually improving performance. It adds stability because we're averaging or voting classifiers. And I think Leo would accept that his point of view is not entirely true, because we know that there are cases where boosting can be effective even with a stable weak learner, but it is suggestive of AdaBoost stabilizing properties. So I'm speculating here, but it seems to me that there might be room for interesting work to be done here to kind of combine these two approaches to get better stability-based bounds, to use Leo's approach to try to argue that AdaBoost is actually increasing stability, and then to use what Sandy and Partha had done and other stability results to bound the generalization error. Okay, so that's the end of that digression. So again, the point is that they're using this other approach. So let me come back now to the approach that we're taking in this work. So again, we're focusing on this weak learning condition. And I'm just going to write capital H, capital script H, for the set of weak classifiers that the weak learning algorithm is using. So for instance, in that little toy example, this would be the space of vertical or horizontal half planes, all of them, the entire set. Or if we're talking about the headline example, then this would be rules that say if a word appears in the document, then predict blah, otherwise predict some other blah. Okay, so this is the space of all possible weak classifiers that we're working with. And just to extract that weak learning condition from the boosting process, what it's saying is that for any distribution that might be chosen by the booster, there exists a weak classifier that could be chosen by the weak learner in this space capital H, such that its weighted error is at most half minus gamma. And we're just talking about existence here, existence of this rule H, not worrying about how to find it. Not worrying about computational costs. Okay, so what I said before is that if the weak learning condition holds, then we know that there are some boosting algorithms, such as AdaBoost, which will drive the training error of the combined classifier to 0. Okay, that's what we talked about before, which means that there must exist a majority vote classifier, in particular this one, which perfectly fits the training data. Okay, so it says something about the data. And it turns out that the converse to that theorem also holds. So if there is any majority vote classifier that perfectly fits the data, then it's actually not that hard to prove that this weak learning condition will hold for some gamma. Okay, so what that means is that this weak learning condition in the binary case is the weakest possible condition that we can have. It's the weakest possible condition. Because if there were any other condition that would be enough to imply that we could drive the training error to 0, then that would mean that there must exist a majority vote classifier that fits the data, which means by this converse that this weak learning condition holds. So any other condition implies this one. So this is the weakest possible condition we could look for. So that's fine. That's the binary case. So finally, what happens? Finally, we get to the multiclass case. What do we do in the multiclass case? So in the multiclass case, rather than there being 2 possible labels, there are k possible labels, okay, k possible categories. And the weak classifiers are still these prediction rules that predict just a single class for each example. Okay, so here's the first most obvious attempt at extending that weak learning condition I had before to the multiclass case. Okay, so it says for any distribution that the booster can pick, the weak learner can find a weak classifier such that its accuracy, the probability of a correct prediction, is at least what you would get with random guessing, which when you have k classes is 1 over k, plus a little bit, plus some small number gamma. Okay, so in other words, you just have to do a little bit better than random. Yeah?
Is gamma optional?
Well, we kind of view it as something that's fixed for the problem, but you know, so there's some. Okay, so we could add it over here. I guess what I really want is there exists gamma positive such that this holds. It could be arbitrarily small. In reality, it's going to have to be at least something like 1 over square root of the sample size for anything to generalize. But for this, just assume it's any arbitrarily small. Yeah. Okay, good. Okay, so so the problem with this first attempt is that it turns out to be too weak. It turns out to be too weak a condition. It turns out that there are cases where this condition holds, but boosting is not possible in the sense that there's no way to drive the training error to 0. You can prove that it's impossible to drive the training error to 0. Okay, so this condition is too weak. So here's a next attempt. The next attempt is to do the same thing, except require that the accuracy is at least a half, rather than 1 over k is at least a half plus a little bit. This is actually the condition used in AdaBoost.m1, which is a multi-class boosting algorithm. And if this condition holds, then boosting is possible. In this sense, we can drive the training error to 0. The problem is this condition is way too strong. It's much, much stronger than random guessing. Okay? Because this is saying the accuracy has to be more than 50%, whereas if you have, let's say, 10 classes, then this is saying that if you guess randomly, you're only right 10% of the time. So this is way better than random. Much too strong. And in practice, what's typically done is to reduce to binary. So you have this multi-class problem. You say, what is the main topic of this article, where you could have k possible answers to that. We can reduce that to a bunch of binary questions. Is the article about sports or not? Is it about politics or not? Each one of those has a yes-no binary answer. Okay? And there are lots of ways of reducing it to those binary questions. This one's called one against all. But there are others that have been considered, and these are practical, but they're not especially well understood. Okay, so here's the framework that we're proposing here. So instead of the booster choosing a distribution, in our framework, the booster instead chooses a cost matrix. So the booster gets to pick the cost of every possible prediction of the weak learner. Okay? So I'm going to denote that C of IL. So this is the cost of predicting one of the labels L on some example I. Okay? So it gets to pick different costs for different predictions of the weak learner. And then the cost of a weak classifier, which gets chosen by the weak learner, is just the sum of the costs on the different examples. So it's the sum over all the examples of the cost on that example of the prediction that was given by that weak classifier. Okay? So now what do we mean by a particular weak classifier being good enough? Before the weak classifier was good enough if its accuracy was at least a half plus gamma, or error at most a half minus gamma. So now instead what we will do is compare the cost incurred by this weak classifier to the cost that would be incurred by a fixed baseline predictor, which I'm denoting by Q. So this is like what we're comparing H to, and if it's as good as that baseline, then we say it's good enough. Okay, so Q is actually not making fixed predictions, but it's allowed to make these kind of soft predictions. Okay, so this baseline predictor is given by a matrix Q of IL, where Q of IL is the degree to which Q predicts a particular label L on an example I. So if you want, you can think of this as a randomized prediction. The baseline is allowed to make randomized predictions. And you can think about this as the probability that it predicts a label. What we have in the paper is a little bit more general, but for the purposes of the talk, that's good enough. So then the cost of this baseline predictor, well, if Q actually is giving a probability distribution, then this is just the expected cost of those predictions. Okay, and if they're not actually probabilities, its cost is still defined by this. Okay? Okay, so there are now two kinds of constraints. There's the constraint on the booster. So first of all, the booster has to choose a cost matrix from some restricted family C. So the booster is restricted in which cost matrices it can use. And the weak learner has to choose H, whose cost is at most that of the baseline. All right, so bringing it together, again, there are these two parameters that define the boosting model. There's the set of allowed cost matrices and the baseline. And now, as before, boosting takes place in rounds, but now the booster chooses one of the cost matrices from the allowed set, and the weak learner chooses a weak classifier. And the weak learning condition now says that the cost of the chosen weak classifier with respect to CD can't be more than that of the baseline. Okay, and at the end of the day, we output, instead of a majority vote, it's just a plurality vote. Whatever label gets the most votes according to the weak classifiers. Okay, so this is the boosting model. Okay, so again, just to extract that weak learning condition, what it's saying is that for every cost matrix that the booster can pick, there exists a weak classifier that the weak learner can find, such that its cost is at most the cost of the baseline. Okay, so let's go back to the binary case and see how we can recover the binary case in this model. So what we do is we choose for the set of cost matrices, we allow the weak we allow the booster to choose any cost matrix such that the cost for the correct label is at most the cost of the incorrect label. So cost of correct can't be more than cost of an incorrect label, which, makes sense. Of course, it should have that structure. And for the baseline, we can define the baseline to give probability half plus gamma to the correct label and half minus gamma to the incorrect label, which just says we should predict the correct label slightly more often than the incorrect label. And now if we let d of I, our usual distribution over examples, be proportional to the difference between what the cost matrix assigns to the incorrect label and what it assigns to the correct label, and you work through definitions, this turns out to give exactly the weak learning condition we had before for the binary case. But what's nice is now we've set things up so it generalizes to the multiclass case. Okay, so now we can immediately generalize to multiclass. Well, let's see the set of allowed cost matrices be again the set of matrices so that the cost of a correct label is at most that of an incorrect label. And for the baseline, what we do is we let the probability of choosing any label, for each example, I, the baseline is outputting a probability distribution over labels. And what we require is that the probability that it assigns to the correct label be at least 2 gamma times the probability it assigns to any of the incorrect labels. Okay, so just predict, same thing, predict correct slightly more often than incorrect. But the thing is that in the binary case, we only had one choice of baseline. But now we have many, many possible choices of baseline. There will be many baseline functions that satisfy these properties. So we end up with a whole family of weak learning conditions, which we call the edge over random weak learning conditions. And they turn out to be both necessary and sufficient for boosting. Okay, so let me explain what I mean by that. So let's say that the space of weak classifiers is boostable if there exists some plurality vote over the weak classifiers that perfectly fits the data. Okay, so this is like the minimum condition for us to be able to drive the training error to 0, that there should exist a classifier of the right form that actually perfectly fits the data. So it turns out that every single edge over random weak learning condition is sufficient for this. So if any of them hold, then the class will be boostable. On the other hand, no single one of them is necessary for boosting, meaning that there are cases where the space is boostable, but that particular weak edge over random weak learning condition that you picked does not hold. On the other hand, if the space is boostable, then there always does exist one which does hold. Okay, so taken as a whole, taking this entire family as a whole, it's both necessary and sufficient. Okay, I said that. Let's see. Okay, so it turns out that, so that's nice, but we might want to have just a single condition which is equivalent to boostability. So it turns out that we can do that. We can form a single condition which is minimal and which is both necessary and sufficient. So to do that, what we do is we allow the weak learner to actually choose which of these edge over random weak learning conditions it gets to compete with. So here's the model that we had before. So before, there's some fixed baseline that the weak learner is always supposed to do better than. On each round, the booster chooses a cost matrix. Weak learner chooses a weak classifier, and that weak classifier has to have cost at most the cost of the baseline. So now what we do is we can change that. So instead of there being a fixed baseline, the weak learner actually gets to choose which edge over random baseline it wants to do better than. It gets to pick a baseline to compete with. And all it has to do is choose a weak classifier, which is better than the baseline that it got to pick. Okay, so, again, we can formalize this. This is the condition we had before. It says for any cost matrix, there exists a weak classifier whose cost is at most the baseline. So now what we're saying is that there only has to exist a baseline that we're doing better than. And it seems like this is giving way, way too much power to the weak learner. But in fact, it turns out that this condition is exactly necessary and sufficient for boostability. So this one condition turns out to exactly capture boostability. And the main proof tool, both here and in everything, is the min-max theorem. Okay, so that was our framework. So we were able to go back and look at a lot of the weak learning conditions that are found in the literature. So we've got 3 different versions of AdaBoost up here. 2 of them turn out to be too strong in terms of the conditions that they require. AdaBoost.mr turns out to be exactly equivalent in this framework. And this is a different algorithm, SAMI, due to Ju et al., which turns out to have a condition which is too weak. Okay, so, all right. So let me talk a little bit about algorithms. So for any fixed single edge over random weak learning condition, we were able to derive a boosting algorithm which is optimally efficient. So the second part of this research was to try to derive algorithms that are as efficient as possible in terms of driving down the training error. So this algorithm that we derived is a generalization of an algorithm called boost by majority, which is due to Freund. For the binary case, it's known to be exactly optimal in the binary case. So the algorithm we developed is based on the drifting games framework, and we have a way of computing the costs. The costs, remember, the booster has to choose these cost matrices, so it turns out those can be computed as expected losses when you assume that the weak classifiers in the future will all predict according to the baseline. So this gives us a simple way of computing those costs. The problem is that this algorithm, like boost by majority, is not adaptive, meaning that we actually have to know this edge gamma ahead of time. And that's the whole problem with this style of boosting algorithm. In practice, you don't want to need to know that ahead of time. So we also derived an adaptive algorithm which is based on that minimal weak learning condition that I talked about before. So this algorithm is analogous to AdaBoost. We use essentially the same framework as before, but we allow the booster to choose a weight alpha t on each round. And then at the end of the day, rather than using plurality vote, we use a weighted plurality vote. Okay, people who have seen AdaBoost this will kind of seem natural. Okay, and there's the algorithm. The point is it's simple and fits on a slide. Okay, so let me talk about some experiments and then I'll be done. So we used this adaptive algorithm and we compared it to 2 previous extensions of AdaBoost for the multiclass case, and we tested it on a bunch of benchmark data sets. And the weak classifiers here were decision trees where we artificially bounded the size of those trees. So here are the results on 6 of the data sets. So the x-axis is showing tree size. Okay, so we tried on various tree sizes of the weak classifiers. So smaller trees tend to be simpler. And the y-axis is showing the test error on a separate test set. And the red curve is for our method. Indranil kept putting new method on these graphs. And I told him that I wasn't going to assign his thesis unless he came up with a name for this algorithm. And now I can't remember what name he came up with. But, okay. So I'll have to call it new method because I'm stuck because I don't remember. Okay, so this is our method, whatever it's called. And then the other 2 algorithms. Sorry, this is test error, yeah. Right. Okay, so if you look especially in the case of small trees, we're often doing quite a bit better than these other algorithms. which is kind of the point. That's the case where we really want to do better, when you're using these very weak classifiers. Okay, here's zooming in on the case where we have, where we're using quite small trees, which only have 5 nodes. So these are really small, simple trees. And on the x-axis, we're showing number of rounds of boosting, and the y-axis is showing the test error again. And so you can kind of see what the problem is, at least in some of the cases, that at least in some cases, these other methods are just getting stuck, like here and here, where they can't go forward with boosting, and our algorithm is able to continue in those cases. Okay, so in conclusion, I talked about a theory of multi-class boosting, and what we saw is that the theory in the multi-class case is maybe richer and more intricate than might have been expected. It's kind of a case where just figuring out the right definitions is not entirely straightforward. So in the multi-class case, there are these whole families of possible weak learning conditions, and we saw that there was an entire family that captures boostability, and we were also able to find a single weak learning condition that captured it. And then I talked about some experiments where we saw that these experiments suggest that maybe this approach can be more effective and efficient than some of the previous ones, especially when using really weak classifiers. Okay, so I'll stop there.